In a remote corner of our galaxy, what appears to be the beautiful, silent death of a star is rewriting the story of how planets are born. For over a century, the heart of the Butterfly Nebula hid behind a veil of cosmic dust, defying all attempts to uncover its core. Until now, breaking, the James Webb Space Telescope has exposed not just the dead star within, but something no one expected. This fading sun is forging the same crystalline dust that once built worlds like our own. If dying stars are seeding the galaxy with the ingredients for life, what else have we missed in the shadows of cosmic death? This is the untold birth of a dead star. At a distance of 3,400 light-years, the Butterfly Nebula spans across the constellation Scorpius, its form unlike any other in the night sky. Two immense lobes of gas and dust stretch outward from a central band, creating the unmistakable outline of cosmic wings. This structure is not the product of a single, uniform outflow, but the result of a complex and violent history. The nebula's double-lobe geometry arises from a dense, dusty torus, a donut-shaped ring that tightly encircles its center. This torus acts as a cosmic barrier, forcing the star's ejected material to flow out along the poles, shaping the nebula's wings and pinching its waist into a narrow, dark lane. The scale of this structure is staggering. Each lobe extends for more than a light-year, with filaments and knots of gas tracing patterns sculpted by winds and radiation. The central torus is so thick and cold that it blocks visible light, hiding whatever lies at the nebula's heart. This dust, composed of silicates and other minerals, absorbs the star's energy and re-radiates it in the infrared, creating a shroud that has kept astronomers guessing for generations. The nebula's symmetry is deceptive. While the wings appear balanced, the underlying flows are turbulent, marked by shock fronts and streams of material moving at hundreds of kilometers per second. The dense equatorial ring not only sculpts the nebula's shape, but also preserves a record of the star's final, chaotic centuries. Every arc and ripple in the dust tells a story of mass, loss, radiation, and the relentless push and pull between gravity and stellar wind. Within this vast, glowing cocoon, the true center remains hidden from ordinary sight. For decades, the dense torus has masked the final remnant of the star that created this spectacle. The Butterfly Nebula stands as both monument and mystery, a vast, double-lobed cloud whose beauty and complexity hint at the forces still concealed within. For more than a century, the heart of the Butterfly Nebula remained an unsolved riddle. Every attempt to find the star responsible for its radiance ended in frustration. In 1880, Edward Emerson Barnard's first observations revealed only a strange, dark lane slicing through the nebula's bright wings, a hint of dense dust, but no sign of a central star. Early photographic plates captured the luminous arcs and knots, but the core stayed invisible, its light swallowed by the surrounding shroud. As telescopes improved, astronomers grew certain that a powerful star must hide within, energizing the nebula's glowing gas. Yet, even with the arrival of the Hubble Space Telescope, direct detection proved elusive. The nebula's central region, cloaked by a torus of silicate-rich dust, absorbed starlight across the visible spectrum. The star's radiation shifted into the ultraviolet, vanished almost completely behind this barrier. Spectroscopic surveys added to the intrigue. Highly ionized atoms, magnesium, silicon, and argon, appeared in the nebula's spectrum, each requiring temperatures above 200,000 degrees Celsius to form. These spectral fingerprints pointed to a searing hot stellar remnant, but left its true nature concealed. Some astronomers speculated about a binary system, others about a star so hot and small that only the faintest trace escaped. Hints surfaced in the structure of the dust itself. ALMA's millimeter wave maps traced a cold, massive ring encircling the nebula's waist, while filaments of gas curled outward, marking paths shaped by hidden forces. The nebula's symmetry, so perfect at first glance, revealed deep imbalances, shocks, ripples, and turbulent flows, all pointing back to a single, unseen source. For over 100 years, the search became a kind of astronomical detective story. Each new instrument offered a fresh vantage, but the core remained a blank. The answer, it seemed, would require a way to see through the dust itself, a tool that could reveal what neither optical nor ultraviolet eyes could find. In the search for answers hidden within the Butterfly Nebula, astronomers turned to instruments capable of seeing what ordinary eyes could not. The James Webb Space Telescope, perched in deep space, brings a mirror 6.6 meters across, large enough to capture the faintest heat radiating from cosmic dust. Its mid-infrared instrument, or MIRI, operates in the crucial window from 5 to 28 micrometers, a range where cold dust glows and the secrets of stellar chemistry are revealed. MIRI's detectors are cooled to just 7 degrees above absolute zero, allowing them to register the faint warmth of silicate grains and organic molecules that would otherwise remain invisible. This sensitivity is not just technical prowess, it is the key to cutting through the dense, cold torus that has hidden the nebula's core for centuries. On the ground, the Atacama Large Millimeter/Submillimeter Array, or ALMA, stands at 5,000 meters above sea level in Chile's desert. 66 radio dishes work in unison, mapping the nebula's coldest material with sub-arc-second precision. ALMA's array can detect the faint rotational signals of molecules like carbon monoxide, tracing the structure and motion of gas at temperatures barely above the cosmic background. In June 2014, ALMA's extended configuration provided a detailed map of the nebula's molecular ring, revealing an intricate system of shells and filaments. The observations pinpointed a massive fragmented ring and uncovered a younger inner ring inclined at 60 degrees to the main structure, evidence of multiple episodic ejections from the dying star. These technological eyes do more than look, they dissect. JWST's MIRI separates the nebula's light into hundreds of spectral fingerprints, each one a signature of a different atom or molecule. ALMA's millimeter wave vision traces the mass and velocity of cold gas, reconstructing the three-dimensional architecture of the nebula's dense regions. Together, these instruments provide a complete inventory of the nebula's dust and gas, from the hottest, most energetic jets to the coldest reservoirs of molecular material. The combination of space-based infrared sensitivity and ground-based millimeter resolution allows astronomers to chart the conditions necessary for dust grains to grow, minerals to crystallize, and complex molecules to assemble. In the Butterfly Nebula, the synergy between JWST and ALMA finally opens a window onto processes that shape both the death of stars and the birth of worlds. Inside the dense, cold torus of the Butterfly Nebula, something extraordinary is taking place. The white dwarf at the core, burning at nearly 220,000 degrees Celsius, drives a process more often associated with the birth of worlds than with the death of a star. Here, under the relentless pressure of radiation and the shelter of thick dust, new grains are forged, crystals that will one day become the seeds of planets. Webb's infrared spectrographs have revealed the unmistakable signatures of crystalline silicates, minerals like forsterite and enstatite, embedded within the nebula's waste. The data show quartz grains, their ordered atomic structures gleaming in the mid-infrared, forming in regions protected from the star's most violent winds. These crystals are not cosmic leftovers. They are being assembled in real time, atom by atom, as the nebula cools and expands. Their size, often exceeding a millionth of a meter, dwarfs typical interstellar dust, pointing to a prolonged and stable growth process unique to this environment. But the chemistry does not end with stone. Amid the silicates, Webb has detected polycyclic aromatic hydrocarbons, flat, ring-shaped molecules built from carbon, the same element that forms the backbone of all life on Earth. These PAHs, rarely seen in oxygen-rich nebulae, are forming here as bubbles of stellar wind collide with the surrounding gas, sparking the reactions needed to assemble complex organic structures. In the harsh glow of a dying star, the raw ingredients of biology are coming together, molecule by molecule. This is the first time astronomers have witnessed such planet-building dust emerging directly from a stellar grave. The discovery overturns the old image of dying stars as mere cosmic endpoints. Instead, the white dwarf stands revealed as an alchemist, transforming the ashes of its former self into minerals and molecules that will travel across the galaxy. Every crystal, every carbon ring is a promise, evidence that even in the heart of destruction, the universe is laying the groundwork for new worlds to come. For over a century, the core of the Butterfly Nebula remained hidden, its true nature obscured by a dense dust torus. Now, data from JWST's MIRI and ALMA have revealed an exposed white dwarf at nearly 220,000 degrees Celsius, surrounded by planet-building dust, crystalline silicates, and PAHs, confirmed for the first time forming around a dying star. These findings show that stars like our Sun not only end, but actively seed the galaxy with materials essential for planets and life. Yet questions remain about how this dust disperses and contributes to future worlds. The combined power of JWST and ALMA has transformed our understanding of stellar death, linking the fate of stars to the origins of planetary systems. As the Butterfly Nebula continues to evolve, its legacy is written in the mineral and carbon grains now traced by science, evidence that even in dying, a star shapes the future of the cosmos.